Hello, I'm going to share some of the principles and methods that I use when I'm converting a scan into a CAD model and show you some of the problems you might encounter as well as ways around them. There's a chat window that lets you comment and ask questions, but I won't be able to answer any of them until the session at the end, which finishes about 90 minutes from now. Everything I'm sharing is based on experience gained over about 40 years, where I've used 3D CAD for about 30, STL files for 20, and scanning services for maybe 10 or 15. I obtained my first scanner in 2016. It was a 3D Systems Sense 2, which was affordable but not good enough for serious engineering work. I replaced this with an Einscan SP, and more recently, for larger objects than the SP can handle, I bought the Einstar. These are perfect for my project to design flight simulator accessories for computer flight simmers. I want to begin by showing you why any scan is going to contain imperfections that you wouldn't want to build into your CAD model, and therefore why the CAD model that you do build from a scan doesn't need to exactly match it. I'll talk about the characteristics of and variations between CAD models, physical objects, and scans of physical objects. A CAD model is the modern version of a blueprint. They've been around since the 1970s, and in a modern manufacturing environment, a CAD model contains all the information needed to make a product. They're generated by design engineers, and they're often used as the core reference for a product, enabling cost and performance calculations, visualization, and generation of computerized manufacturing data. One form of manufacturing data that comes from a CAD model is an STL file, commonly used now for 3D printing. It's a file format invented for that purpose in 1987 by 3D Systems. Where the STL file contains a cloud of points representing the surface of an object, it was an obvious choice as the output format for 3D scanners, which also generate point clouds. The normal process flow is to put all the design and engineering ideas into the CAD model and then make a physical version of that and use the model as a reference when you measure the physical part. When you're building a CAD model from a scan, sometimes called reverse engineering, you probably have limited or no knowledge of the original designer's intentions. You can't tell whether the scan part is right or wrong, but you're going to trace over it anyway to build a new CAD model. Even if the part has just come off a perfectly calibrated printer, it will not be identical to its CAD model parent. A CAD model is perfect. Straight lines are dead straight, flat faces are perfectly flat, and so on. A physical object isn't perfect. Lines that should be straight are wavy, flat faces are warped, and so on. While these deviations are usually small, possibly too small to see, they will get picked up on a good quality scanner. The imperfections arise from manufacturing processes working within tolerance bands, and from wear and tear, distortion, being overloaded or heated and cooled, repairs, coats of paint, and so on. At this point, you might be asking yourself, where the original CAD is perfect and the physical part isn't, why would you ever want to trace over a scan to make a new CAD model? One good reason is to create something that's otherwise unobtainable. It could be a clay part that you've modeled by hand. Or, if it's a vintage car part, you could borrow the part you need, scan it, make the CAD model, and then make a new part. Another reason is to make sure that your newly designed product fits properly to an existing object. This could be a 3D printed phone holder you've designed to fit in your car's cubby box, or a motorhome shell that has to fit perfectly to the cab of a mass-produced truck. In each case, while most of the design is original, the interfacing area is copied, and to make a good copy, you need to scan the mating part and model it in CAD, using the scan as the template. You can also use the scan as a rough template to create something similar to the object. My friend wanted to build a flying scale model of a plane, so we bought a small plastic kit, scanned it, and made a CAD model. The model was approximately the same, but simplified in many areas. I've spoken about imperfections in physical objects. There are also imperfections that arise as you scan the part and post-process the scan, and they're influenced by the limitations of the scanner and the operator, and what's done to the mesh before the file gets saved. When you know your scan has all those imperfections and defects, are you supposed to try and reproduce them in the CAD model? Most of the time, thankfully, you don't. You can judge what should be straight and what shouldn't. You'll know why you're designing the product and which features matter and which ones don't. Let's say you want to model up a new propeller to replace a damaged one. The scan is going to pick up all that damage as well as all the wear and tear and those defects in manufacturing. Of course, you don't want to model the damage. You've got 3 blade scans. You make one good blade from those, and then maybe use other tools to measure the shaft, model up a new hub, duplicate your new blade CAD model, and make a perfect balanced propeller. With the motorhome, you're going to make one expensive mold to build those bodies to fit the truck cabs. They're mass-produced and you have no control over the build tolerance, and you can be sure they won't all be exactly the same. They could be 10 millimeters different from one example to the next. So you scan the cab you have got, model it as you think it was intended, with the cab central on the truck chassis, and then you offset the cab surface by an amount that you can confidently fill with gap-filling sealant. In the next part, I'll show you some examples, and they're all related to this joystick project I'm working on. I'm looking to scan features from this gaming joystick on the left and build them into a new model that should look something like the light aircraft joystick on the right. The gaming joystick contains a button pad and PCB that I want to build into the new handle. To get a scan in 2023 is more affordable than ever. Before about 2010, scanners were connected to floor-mounted articulated arms with position sensors on each joint, so a computer could calculate the position of the scanning head. As computing power has advanced, scanners can work out positional changes just from the images they're collecting. Did you know you can create a 3D scan using an iPhone or an iPad? It's no good for the work I'm doing, but you can scan your house or garden with one and plan a makeover, and I'm sure there are people out there who have done much more than that. At the other end of the scale, you can get handheld scanners that are suitable for metrology applications. In the examples coming up, all the scans are done on the SP, which is well suited to these smaller parts. When you're scanning to create a template for your CAD model using a structured light scanner, you need to be aware of your scanner's limitations. These scanners typically have elements spaced out on the active face, like this, emitting light and taking in reflections. To acquire any surface data, all these elements need to be in line of sight of the surface feature. And this works well on convex or flattish or external features, but holes can be a challenge. When you're scanning a small hole, the only part of the inner wall that will get scanned is just around the top. There's no way that all 3 elements can detect the surfaces further down. You can tilt the scanner in different directions, but you'll still only capture the top edge, and this can be a problem if you need to model these holes in CAD. If the scanner doesn't detect the center position or the depth, what can you do? For the depth, you need to resort to a traditional depth gauge, which you can also use to double check the internal diameter. For the hole position, there is a trick I've not seen others using, which is to plug the hole, leaving some of the plug exposed. The exposed part scans easily, And you could use a dowel, or if it's a screw hole, you can put the screw back in. Drill bits are also quite handy, as are rubber bungs and cocktail sticks. The rule is that if you can see it, you can scan it. And obviously, you don't want to use a loose-fitting plug. There's a similar problem with deep grooves. Unlike a hole, you can't plug a groove. So if your scanner's line of elements are at right angles to the groove, it won't capture as much data as if it's in line with the groove. Other preparations when you're scanning, apart from of course markers and scanning spray if necessary, a couple of other tips are to take flexible or distorted parts and fasten them down so that they maintain the correct shape. If you do use scanning spray, don't use too much. A buildup of spray on the surface will change the shape of the part. When you're creating a mesh, always save it as non-watertight. Here's a non-watertight mesh, and I'm going to use an auto hole filling option, which is what happens when you make a watertight mesh. While you can see that it does actually fill the holes, the infill surface isn't the same shape as the part. This automatically generated surface will not help you when you're building a CAD model, and this is true whether you use flat, tangential, or curvature settings. With all post-processing options, minimize the amount you use for smoothing, simplification, and optimization. These can be helpful, but don't overuse them because they make the mesh a different shape from the part. This is an exaggerated example of simplification, but you can see it produces a low poly model, which is a distant cousin of the original scan. Mesh optimization smooths out curves, but again, it changes the shape. Smoothing is another. When we smooth this corner, it looks nicer, but it's not the shape that the original part was. If you're making a CAD model, the scan doesn't need to look nice, but it should be as close to the physical part shape as possible. A small amount of smoothing might be necessary to get rid of some obvious lumps, but definitely don't overuse it. The basic requirement for the CAD system that you use is that it must be able to import a point cloud and create sections on the cloud and be able to move it around. If you want to accurately model organic shapes, you'll also need surfacing tools. There are dedicated systems and plugins for mainstream CAD packages that help users generate CAD entities from scans, finding best fit planes and surfaces and so on. There are other webinars in the Shining 3D collection that cover this, including Solid Edge and Geomagic Essentials. If you have the budget, there are some great tools out there. The system I'm using is called ZW3D. It's a well-specified system that works similarly to SolidWorks or TrueFusion and Rhino, and it does have a toolkit for working with scans. The main tool I will be using is the one that creates a cross-section between the scan and a plane. I'll be using these sections as the basis for constructing sketches and then surface entities using general CAD surfacing tools. And this isn't a surfacing course. To put these ideas into practice, you'll need to be able to use the tools in your system. Regardless of which CAD system you use and which plugins you have, the process I use is simple and it will work for you. The key stages of it are: import the scan and align it to the CAD construction axis. Create a plane where you need a section through the scan. Create the section. Hide the scan. Create a sketch on the section plane, and then trace the section using lines, arcs, and splines to make a refined version of the section. Repeat this as necessary in different positions, and then build CAD entity surfaces using the sketches. Here I'm using the Einscan SP to scan one of the handle moldings, and in fact all of the parts in this
webinar was scanned on the SP. I'm using it to scan a handle molding, and it's a black shiny injection molding, so I've sprayed it with dry shampoo. I've got the scanner on a tripod, and I'm using turntable marker mode. The scan process is speeded up because in total it takes about 30 minutes from very start to very finish. You can just see me moving the part around there to get a better view. What I'm doing here is getting all of the outside and a bit of the inside, so that when it comes to turning it over, the inner features will have something to align with. Not looking bad. Keep going. Turn the part over. As I mentioned in the introduction, any scanner is going to have a problem getting into deep grooves. And what I find as this scan nears completion is that some of those pits and crevices just won't pick up. This isn't going to be a problem for me because when I'm making a CAD model of the part, I can use the outer surface as a reference and then offset it if I was making a model of this part. So the fact that I'm missing some of the surfaces internally isn't going to cause a great problem. Obviously you can't 3D print, but I don't want to autofill the holes because we know that that'll change the shape of the ribs. I could have scanned this with the Einstar, but to be honest, for a part as small as this, the turntable is a great convenience, and the SP is possibly more accurate at very fine resolutions. So here's the mesh. You can see that there are bits of engraving detail visible. The recycling logo and the cavity numbers and part numbers. This is the original mesh with no post-processing applied. Some of those screw bosses, the screw holes, as I mentioned, haven't come out very well on the inside, but the outside of the bosses is just fine. This is the part where it starts getting exciting. I'm going to import some scan data to the CAD system and align it with the CAD system axis. I'm using ZW3D here, but you could be using any system that's able to import a cloud of points. So the first thing I've done is created a part, and now I'm importing the point cloud. Point cloud's imported, but it's not visible, and that's because it's got an almost randomly created 0 position. So the first thing I want to do is line that part up meaningfully with the construction axis in the CAD system. The first step I'm going to take is just to roughly get it somewhere near so that I can see both the scan and the axis, and then move it around and have a look at the scan to pick up some useful faces which I think I might want to use as a reference. The planar mating face seems like the most obvious one. The first step is to create a plane on the face using 3 points, which I'll be picking up from the scan directly. and then I'm going to do a frame to frame or axis to axis transfer, which is going to move that plane to align with one of the planes on the construction axis. In my system, possibly yours too, the move isn't recorded in history, so I don't need any of the geometry that I created for the transform. I'm just checking the part now to see if it is aligned. Now there's a bend here in the part. We're not going to use that for the planar reference, so everything's going to be concentrated down this bottom end. I'm still checking that position, and I'm doing it by creating a plane offset from the construction axis, and then I'm going to create a section through that plane and analyze the section. I'm drawing a horizontal line on a sketch, and then I'm going to compare that horizontal line with the section that I've just created. And what I see is that the cross section is waving in and out of the perfectly straight horizontal sketch line. Now we're in a position to align the scan to the x-axis. I'm going to draw a horizontal line there, and then another line which is aligned as well as I can with the edge of the scan. Measure the angle between these two lines, and then rotate the scan by that amount. So I exit the sketch, delete it because it's only construction geometry used for moving the scan, and then I rotate the part about the z-axis by the amount which I measured. Now when we go for a true view on that, that bottom face looks much more like horizontal to me. And so now I can cut that section to find the center of the circular face to move the scan. But I get the plane where I want it and then cut the section. And when I've cut the section, instead of making a straight line this time, I'm going to create a sketch with a 3-point circle. Because this is an injection molded part, I expect the ends of the circle to possibly be drafted straight lines. So I'm going to pick the bottom 3/4 of that circle for my 3-point arc. So positioning that circle there, what I see is that the cross section through the scan is weaving in and out of the sketched circle, which is a good sign. It means that I'm not too big and not too small, but I'm just about average. And I put a point at the center, which is where I want to move the scan from to align it with the absolute zero on the construction axis. So a simple point-to-point move of the scan and delete the construction entities. Now, I've gone to quite a lot of effort to get this scan aligned with this axis, and you might wonder why, because I haven't actually constructed any surfaces or entities from it, but it's really important. When you're building any model in CAD, you want to base it off some reference within the CAD system, and the most basic reference is this coordinate system. If you're tracing around the scan, then it makes perfect sense to align the scan to the coordinate system so that you're not forever trying to use some ethereal reference on the scan, and you don't want to build a coordinate system in the random position that the scan turns up. So align the scan. When you align this and when you align every other scan that you import, you can assemble them together like CAD entities in an assembly. It really is worth the investment of time. I know this has been speeded up in part, but if I hadn't been doing the commentary, it would have taken about 10 minutes. And what you're watching in the background is just a final check to see how well the part is aligned to that system. I've drawn a horizontal line there. Sorry, it's not horizontal, it's point to point. And there's a horizontal line. And when I measure the difference, I see that there is still just a tiny amount, 0.17 of a degree out. So my x-axis wasn't perfectly aligned according to this section. So I think I'll just rotate it one more time. And I know it might seem tedious, but it will pay off when you start doing the CAD modeling. There's just one final step. I want the z-axis to go up the handle. So I'm going to rotate the whole scan by 90 degrees. And that's my alignment of this part finished. Now that the part's set up on the CAD construction axis, I want to start finding the profiles and modeling some of the features within the joystick. Not the entire joystick, of course, that's too complex for me, and I don't want to make a copy of it, but I do want these ribs here because this shaft from the next part mates in here between the two clamshells. Also at the top I'm going to want the PCB mounting, but I'll come to that later. For every feature that I'm going to model on this scan, I'm going to use the same technique, which is to make a plane that cuts through the scan where I need to find a profile, then make a cross section on that plane intersecting the scan, and then create a sketch on the plane. And I'm going to draw CAD entities within the sketch which trace around and correct errors in the cross section through the scan profile. So the first thing I'm doing here is making a plane to cut a section through the ribs, which is then going to let me find the center locations of the ribs. You can see them there with their wavy little lines. What I'm going to do is draw horizontal lines, which are truly horizontal to my CAD construction axis with which this scan is aligned, and put a sketched horizontal line through the center of each rib. This sketch that I'm doing now is actually an extra step. I'm doing it because it's a very easy way to find out where to put those planes that I want for making the sections. So it's a CAD sketch, you can move the lines around, and I'm putting each one where I think the approximate center of the rib is that I want to section. The next step is to use the CAD coordinate system XY plane as a reference, and then create a plane offset from that through a point where the point is the end of one of the sketched lines. So that's selecting the XY plane and then picking a point for the plane that I've just created and repeating. So once again we're speeded up 10 times, and the last plane is perpendicular to a line that I've drawn. So now we've got the planes, we can delete all the construction data and restore the scan. And move straight to making a cross section through the scan data where we have one section for each plane. On my system, you can make them all at the same time. It's taking a moment. I wish it was speeded up by 10 times. Now hide the scan and you can see a set of sections there, each one on a plane and each one showing the profile of the scanned ribs. I'm going to inspect those sections now by taking a true view on the CAD XY plane. And what I see is that they're not perfectly concentric. So I'm not going to make an individual cutout for each rib because I know that they'll be misaligned with each other. And that's because the molding that I scanned isn't perfectly straight. Actually, those features mate onto a shaft, which is a separate component, which I know is straight. I've also modeled that. So I'll cut these semicircles out with the shaft at a later stage. And for now, I'll just make the rectangular sections of the ribs in preparation for cutting them out later. So for now, I'm going to make a sketch, which is as simple as they get. It's a rectangle where the top of the rectangle is lined up with the first rib's top. So I just constrain the sketch to the section. And I'm going to check the measurement of that from the center, bearing in mind that I don't want to reference the sections in the final model. And I see it's 3.61 millimeters. I think it probably ought to be 3.6, which will do for me. So I will reconstrain it back to the CAD 0 reference. This means that I'll be able to delete the scan sections later without damaging the sketches. Now, normally I would delete any construction data used for transforming the scan, and often I'll delete the sections through the scan as well. But on this occasion, these rib sections are going to be useful for later because I've still got many sketches to produce. So I'll put them in a set and hide the set rather than delete it. The next stage is to take that rectangle sketch that I made and to extrude that into solids, where each solid is equally spaced about the planes that I cut those sections from. So I'm projecting it to the plane, adding 0.7 millimeters one side and taking off 0.7 millimeters the other side to make the first rib, and then repeat that to make the series. If you're sharp-eyed enough, you probably spotted when we had the sections on the screen that not all the ribs are the same height. So when I put the scan on top of these rectangular ribs that I've just made, I see that some of them are different heights. One way to correct that is to measure, as I did for the first one, and then do an offset of the measured amount. But actually it's easier to just use the scan as a visual reference and to bring the ribs up to the right height. Now this scan is of an injection molded part where the faces of the ribs are drafted by about 1 degree per side. And if I was making an injection molding, I might want to copy that draft as well. In this case, the part's going to be 3D printed. It doesn't need any draft, and so I'm not going to apply it. At this point, I'm going to save the model. Before we move on to more complex surfaces, let's have a look at another mechanical, simple part, which is the printed circuit board. I need a package model of that. And so, as with the joystick handle, I've taken a scan, imported it into CAD, aligned it with the CAD construction axis, created a plane, off that axis, cut a section through the scan, and what you see now is a sketch of the outer profile of the printed circuit board being drawn using the scan section as a reference. One thing that you notice in the printed circuit board is that this central feature, which is supposed to be a circular hole with two intersecting rectangular slots with rounded ends, it doesn't look as if it's scanned very well, and indeed it hasn't. You remember what I said about the scanner not being able to see into holes very well. Well, remember these slots are just 2 mm wide, and so it's getting towards the limit of the scanner. So I'm doing my best to construct a sketch here of something that will do for the packaging model. And I'm going to do what I can at this stage, but I will come back to this later because there is a trick to improving things that haven't scanned very well. Another set of features that haven't scanned very well are these small mounting holes. You see the 3 circles or rough circles across the bottom. I know that the outer 2 are supposed to be the same size, and they're not even circular. So what I'm going to do later is use the mating part, which has got screw bosses which align perfectly with these holes, and I'm going to use those screw bosses to find the center. But for now, I'll create a sketch which approximately aligns with what look like the holes. For the remaining elements of my PCB packaging model, which is the components on the PCB, after extruding my first sketch, of course, to make the board itself, I'm creating a plane and cutting a section through the scan on the plane, hiding the scan, and then creating a sketch on that plane and tracing over the scan sections and approximating them to make them neat. So there's the first switch, which I happen to know from the reference manual is 6 by 6 millimeters. You can see it just about perfectly lines up with the scan, all but one of them's out of position. And then extrude the height to match the scanned height. It's a packaging model, so I'm just eyeballing this. And then after repeating that for every component that's on the board, I end up with a complete populated PCB packaging model, which I can put into my final assembly and use as required to check fit and clearances. A few minutes ago we talked about how the scan hadn't picked up those small holes to the point that I could find the center. So here's the scan of the bezel in position on the PCB, and the bezel has got those screw bosses. So once again, I'm just eyeballing that with a true view to create a sketch which is aligned with the PCB. I'm going to make a plane through the sketch, offset from the plane, cut a section through the scan on the new plane, hide the scan, and create a sketch on those sections. Now, the scan here is so good that I don't have to eyeball anything. I can create a 3-point circle on that scan section, and then I'm going to draw a vertical line down from that and create a second circle, and I'm going to use that vertical line to make sure that the two circles are aligned with each other. and then move on to making the final circles that we need, which is this location peg, which is actually off the center line, and then the third screw hole, again using 3-point arcs. You may have noticed that they're all coming out at almost exactly the same diameter, which is to be expected of the injection molded part, but also the scan accuracy is really good on these easy to see surfaces. And while I'm at it, I'm finishing off that central feature where we've got the crossing elements. You notice there's much sharper corners here. This is of course the plastic piece that fits in, and we just need to make a big enough clearance hole for that. So with that sketch made on the mating plastic part, we're ready to transfer the newly sketched features onto the PCB, which is still superimposed. You can see the old holes that I guessed and the new holes that I've drawn accurately, and so I'm just going to replace the incorrect features with the correct ones. Now we can regenerate the PCB package model with all the holes in the right place, confident that we can use those holes later to align with the bezel once we've constructed that. So far we've looked at rectangular and fairly simple extruded shapes. What I'm doing here is something that's a little bit more complex. This is one of the handle surfaces, and I'm using a facility in my CAD system which is similar to Geometric Essentials, which claims to be able to project a surface onto a point cloud. So I'm taking the complete point cloud minus the inside, so there's no ribs or bosses there. The surface needs also a set of curves that it must run through, so I'm just tracing the edge of the part there and setting the surface up to do its projection. What you see when you look at it is one single surface for the entire part, and while it looks like it's done a good job, the surface is also quite rippled around the edges, and of course you would never make a surface like that if you were modeling in CAD. You would make a part like this out of tens or possibly hundreds of surfaces, so you'd never do it from one single one. The reason for showing you this is to demonstrate the difference between automatically wrapped surfaces that these plugins will give you and manually generated surfaces using the native tools available in your CAD modeling software. The surface here is set to let you visualize the smoothness of surfaces, and the one on the left is an automatically wrapped patch around the end of the joystick, and the one on the right is being generated now using native tools and entities that have been created the way I've described in the earlier part of this presentation. What you see, or will see, is that the number of control points on the manually generated surface is far fewer than the number on the automatically wrapped patch, and it's certainly advantageous to have the surfaces as simple as possible to give the amount of curvature that you need. When you have the number of points that are on the automatically wrapped patch, it means that it's probably rippled and probably not the shape that you actually want it to be. I've overlaid this on the scan, and I can tell you there isn't really much to complain about. Here's a much more controlled way of creating a surface on a point cloud. Rather than using the point cloud itself as the target for the wrapped surface, I'm going to generate a set of points just in the patch that I want the surface to cover. So I'm drawing the points at 5 times normal speed, just on the patch that I want to apply the surface to, and then selecting those and choosing to wrap a surface with a U and V degree of 3, which is as low as you can get. And when we look at the control points on that surface, the number of them is very low, which is what we want for a simple surface. That technique comes in especially handy for the next surface, which has got enormous holes all over it where the buttons poke through. I can still pick points from the surface, and obviously I can't pick them where we've got holes, but that's okay. The surface that's going to map onto this collection of points I'm drawing on will bridge those holes. Now, this surface through these points, while it does actually go through the points, if I make a symmetrical copy of it about the center plane, there isn't a smooth transition from left to right. So what we need to do is somehow change the edge of the surface, which is, you could actually do that, but what I'm going to do is use that surface to create some more sections in the same way as previously, and then on those sections sketch some cross sections that I want to use for constructing a new surface. Now the new surface is going to deviate from the scan a little bit further, but it will be continuous from left to right, and that is what I want in the end. Once again, I'm creating a set of planes which I'm using to create a set of sections, although this time through the surface. And then on each plane I'm making a sketch, and that sketch is the profile of the final surface that I want. So that surface doesn't look too bad, although when I do a centerline section, I find that it's just a little bit deep into the scan. And again, I'm eyeballing this. I'm not taking any measurements, and perhaps I should, but I'll create a new spline here, which should better represent the scan section, and then shift the surface onto that new spline and see how the result comes out.